The other test we have for absolute convergence is called the ratio test. So instead of looking at a limit of ratios, we're going to look at a limit of roots of the numbers in the sequence. So we'll take our formula for the number a sub n. We will look at it in terms of absolute value, so throw away any negatives you might have in there. And then depending on what n is, we will take the nth root of that term. And the results of this test are similar to the results of the root test, of the ratio test. So if this limit is a number less than 1, then the original series is absolutely convergent. If the limit is greater than 1 or infinity, the series diverges. And if the limit is equal to 1, the root test says nothing, not enough information. So again, I like to think of this in terms of the geometric series, since if I applied the root test to the geometric series, in every single one of these cases, my limit would just be that common ratio, r. So r less than 1, series converges. R greater than 1, series diverges. R equals 1. In the geometric series, that diverges, but in general, we would need more information. So if the limit of the nth root of the absolute value of the nth term equals 1, then we would need more information, and actually the root test would also not work here. So this is most useful when we are taking a series and the nth number in my series is something that I already know is an nth power. Here is a series where I'm adding up all the fractions starting at n equals 1 to infinity. The fractions have the formula numerator 2n plus 3, all on denominator 3n plus 2. That whole fraction raised to the power n. So I already know this is an nth power. Taking an nth root of that is very simple to do. I just cancel out the nth power. I've got what is the limit then of 2n plus 3 all on 3n plus 2. Well, I can rewrite this as 2 plus 3 on n divided by 3 plus 2 on n. That's going to 2/3. So this series is convergent. All we had to do was use the root test.